In our solar system, astronomers recognize two kinds of planets. Terrestrial, or Earth-like planets, are small and solid, and they're close to the sun. Jovian, or Jupiter-like planets, are gas giants, very large and far away from the sun. These types of planets differ in chemical composition, with inner planets being made of rock and metal, and outer planets of hydrogen, helium, water, ammonia, and methane. The key takeaway from this is the link between these three properties: location, size, and chemical composition. Looking at our solar system, it seems sort of obvious to conclude that our planets formed more or less in their current orbits out of the different materials available in those places, and that the availability of materials determine the planet's sizes. But let's look a little more at the formation process. Stars, including our sun, form from diffuse clouds made mostly of hydrogen and helium gas, with smaller amounts of rocky and metallic dust grains, as well as icy crystals of water, ammonia, and methane. And I'm going to call water, ammonia, methane WAM. These clouds are enormous, and their great mass exerts strong gravity, pulling the cloud tighter together. Some matter falls to the center to form the star, while other matter orbits the center in a flattened disk or pancake-shaped distribution that spins as it contracts. We can see examples of such disks around young stars with sufficient frequency and clarity to be quite confident of the general outlines of this theory. Here you see a few examples of these clouds called protoplanetary disks. And in these particularly, you see the effect of a hot center with a cooler cloud around it. This second picture, or this second set of pictures, is much higher resolution, although it's showing you very much the same kind of objects. I shouldn't say little, they're really pretty big. This second set of pictures is much higher resolution, and what it shows you is incredible structure within the disks. The idea is that you're looking at these pancake shapes from many directions. The round ones, you're looking from the top, and the more cigar-shaped ones, you're looking from the sides. The ring-like appearance, and by that I mean the things that look a little bit like a target symbol, concentric circles, one around the other, dark and light. Okay, that ring-like appearance is thought to result from planet formation. As a planet develops, it gathers up the fluffy material at its orbital distance from the central star, literally making up the planet by accreting, letting that matter stick together, as it opens up gaps in the fluffy cloud material. So we think that there are probably planets, or at least protoplanets, embedded in the dark gaps between the glowing rings. I can't resist pointing out how spectacular these images actually are. Remember the scale model we discussed a little while ago, the one where the sun was an orange and the solar system, our solar system, was spread out over the size of a college campus? And remember that the nearest star was thousands of miles away, and other stars were many, many thousands of miles away. So looking at actually seeing in your picture, the detailed ring-like structure that you see in these images is comparable to photographing the features of a college campus and photographing them from many, many thousands of miles away. Also, here's one idea to save for a little later. While you might think that something chunky like a planet would be easier to photograph than cloudy fluff, it turns out that the opposite is actually true. Planets in these pictures would be invisible dots. Look in those little dark gaps in the rings, and you really don't see any dots where those invisible dots would be, right? So the planets in these pictures would be invisible dots, while the cloud, because it has a larger surface area, is the thing that is easier to see. But let's go back to ideas of planet formation. And let's think for a moment about solids and gases. What makes a gas act like a gas is that the molecules bounce around freely instead of sticking together. Therefore, if your process demands that matter stick together into planets, what you need are solids, bits of ice and dust to get the process going. So we need solids to accrete planetary cores. And now let's think about the effect of temperature. Close to a star, where it's warmer, like where Mercury, Venus, and Mars formed in our solar systems, water, ammonia, and methane. Remember, that's what we're calling WAM. The water and ammonia and methane all evaporated. And so they couldn't be incorporated into the clumps of solid rock and metal they're created to make the inner planets. But farther out where it's colder, WAM is icy and joins the rock and metal in making planetary cores. The addition of WAM increases the available solids so that the outer cores, the addition of WAM increases the available solids to make the cores so that the outer solar system planets grow huge, with Uranus and Neptune becoming 15 and 17 times the mass of Earth. The gravity of the biggest cores is sufficient to attract hydrogen and helium gas, raising Saturn and Jupiter to 95 and 318 times the mass of Earth. With their great internal pressure and heat, the outer planets have melted the ices of their formation. So what they have is turbulent, cloudy atmospheres over massive liquid interiors. And in the inner system, what you really have in the inner disk are just the little cores without great big thick atmospheres atop them. You have thin atmospheres. And this might again seem a little funny because we think of Earth's atmosphere as being somewhat thick, but in reality, compared to these others, it's a pretty skinny little atmosphere. So here's that artist's conception of what the process might have looked like, showing clumping of planets and protoplanets, showing clumping of protoplanets into full-fledged planets of many different sizes. And you can see very, very tiny ones that might be protoplanetary or inner terrestrial planets. You can also see this lovely, charming example of an outer planet showing its rings. And I'll just point out that the moons might be forming in the gaps of the rings in an analogous process similar to planets forming in gaps in disc-shaped ring structures around stars. So it's kind of like the planet system is a little bit of a mini-me in solar system formation. So now let's think about those resulting planets. While the solid surfaces of the small inner terrestrial planets offer stable platforms with high concentrations of the chemical compounds, chemical components that we think life needs, and therefore are promising as habitable spaces, we believe that the Jovian planets, with their dilute chemistry, their violent weather, and nothing solid to stand on, are probably pretty unlikely abodes for life. Jovian moons may be a different story. And in our system, all the Jovians have extensive moon systems that share enough terrestrial properties to at least be speculative long shots for habitability. So now let's think a little bit about generalizing formation theories. This brief explanation of how our planets formed is part of a more general theory of the formation of planetary systems. It's problematic, however, because the defining idea of science is that theories must be tested. But you can't test a theory by comparing it to the same data set that it was developed to explain. Of course it does a good job of explaining, of course our theory does a good job of explaining our solar system. That's what we invented it to do. So we need more examples of other systems so we can compare the properties that our theory predicts to the parameters of those other systems. And this is important because we need a formation theory that is valid for all solar systems, our solar system and exosystems, if we're to use our theory to help us with the really important question, are exosystems like ours common? So let's think for a minute about a few of the important aspects of these big questions that we think we could answer if we had a reasonable number of other systems to observe. What I'm really talking about here is the idea that from all this theory that we've describing, we have to extract some measurable parameters. And then we can ask, how much variety might there be between systems? Would different starting conditions, if you had systems that started in somewhat different circumstances, would they result in systems very different from our own, even though really the same basic physical processes are taking place? And when we talk about what we could measure, we're really asking, can we measure aspects of exoplanets that show exoplanets to be like our planets, or are they very different? And is the architecture of our system typical? And by that we mean, do we find the expected kinds of planets at the expected distances? Little ones close in, big ones far out. Finally, how stable are solar systems? Even how stable is our own system? The stability we see in the current layout of our system, and our current systems is pretty stable in the way it's arranged. But that might not be true of other systems, and it might not even describe the many billion year history of our system. Do planets really remain in the orbits in which they formed, or do they migrate inward? Do they migrate until they crash into their sun, migrate inward? Do they migrate outward until they are lost from their system? Variety and long-term stability have serious implications for our search for life.